तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. Today is the first lecture of the Module 3 on analysis of members. Till now, we have studied the material properties, the prestressing systems and devices, and the losses of prestress. Today, we are moving on to the analysis of prestressed concrete members. First, we shall study the analysis of members under axial load, and under that we shall study the analysis at transfer, analysis at service loads, analysis of ultimate strength, and finally we shall study the analysis of behavior. The geometric properties that we shall use is shown schematically in this figure. On the left, you can see a typical axially loaded member where we may have both prestressing tendons and non-prestressed reinforcement. A is the gross cross-sectional area of the member. Now, the prestressed member consists of the area of concrete, which is represented as AC. Then it consists of the area of the non-prestressed reinforcement, which is represented as AS, and it also consists of the area of the prestressed tendons, which is represented by AP. Thus, A is equal to AC plus AS plus AP. Another geometric property that we shall use is the transformed section, when the reinforcement and the prestressed tendons are transformed to equivalent areas of concrete, and we add that to the remaining part of the concrete. The total transformed area is termed as the transformed area of the section. It is represented as AT, and AT is equal to AC plus the modular ratio times AS plus the modular ratio of the prestressing tendons times AP. The modular ratio for either of the reinforcement or the prestressed tendons is given as the ratio of the elastic modulus of the steel divided by the elastic modulus of the concrete. The transformation is done when we study the stresses under elastic analysis. Prestressed concrete members under axial loads only are uncommon. Members such as hangers and ties are subjected to axial tension. Members such as piles may have bending moment along with axial compression or tension. In this figure, we see on the left hand side the floor at the bottom has been suspended from the floor at the top by hangers. Now, this hanger is subjected to axial tension, and it needs to be pre-stressed to have an area of the member within a certain architectural limit. On the right hand side, we see a pile which is subjected to axial compression, but piles can go to axial tension also when there will be uplift under high lateral force on the building, and also the piles are subjected to shear and it can be subjected to bending moments. In these sketches, we have shown only the vertical forces. The ties are members which are horizontal and are subjected to tension. A prestressed axial member may also have non-prestressed reinforcement to carry the axial force. This type of members are called partially prestressed members. We shall also come back to partially prestressed members for flexure. These type of members are somewhere in between the reinforced concrete members and fully prestressed members. The partially prestressed members have both prestressing tendons and non-prestressed reinforcement to carry the forces. The study of members under axial loads gives an insight of the behavior of a prestressed member as compared to an equivalent non-prestressed reinforced concrete member. Now, why at all we are studying members under axial load if such members are not common? The reason is that there are some basic differences between a reinforced concrete member and a prestressed concrete member, which is easy to understand if we are studying the axially loaded members first. And this gives an insight into the effect of prestressing on the behavior of reinforced concrete members. Now, the one we are studying right now, in that case we will neglect any eccentricity of the prestressing tendon with respect to the CGC. That means we are considering that the CGS lies at the level of the CGC. Now, the analysis refers to the following. The first, we shall study the permissible prestress based on allowable stresses at transfer. Earlier, we had known that the load stages in a prestressed concrete member can be divided into several stages. The first one is the stage at the transfer of prestress. Second is the stage during transportation of the prestressed member from its casting site to its permanent position. Third is the stage under service loads, and finally, under some extreme event, it can be subjected to ultimate loads. Now, for all these load stages, we need to study the stresses or the strength. Now, here we are first studying the stresses at transfer, and based on the allowable stresses at transfer, the maximum prestress is determined. The second, we are studying the stresses under service loads. Now, in these stresses are compared with the allowable stresses under service conditions. Remember that the allowable stresses can be different at transfer and under service conditions. We have studied the allowable stresses under the module of material properties. Third, we shall study the ultimate strength. This is compared with the demand under the factored loads. That means in a limit state design, we compare the ultimate strength with the demand under ultimate loads, which is the factored loads times the characteristic loads. And finally, we shall study the entire axial load versus deformation behavior to understand the full property of the prestressed concrete member. First, we are studying the analysis at transfer. The stress in the concrete can be calculated as follows, that the stress is given as the ratio of the prestress at transfer after short-term losses divided by the area of the concrete. Now, in this expression, we have not considered any non-prestressed reinforcement. Just note that we are considering a negative sign for a compressive stress under the prestressing force. In presence of non-prestressed reinforcement, the stress in the concrete can be calculated as follows. The stress is given by the prestress at transfer divided by a transformed area, which is equal to the area of the concrete plus the modular ratio of the reinforcement steel times the area of the reinforcement steel. This denominator is higher than just the area of the concrete. The permissible prestress is determined based on Fc to be within the allowable stress at transfer. That means we have to apply the prestress up to a certain level such that the stress under transfer is within the allowable value at transfer. Next, we are studying the analysis at service loads. The stresses in concrete can be calculated by this following expression, where the stress is equal to minus PE by AC plus minus P by AT. PE is the effective prestress, which is after the long-term losses. AC is the area of the concrete. P is the external force, and AT is the transformed area. Now, if we have a tensile force, then we shall use the plus sign, and if you have a compressive external force, then we shall apply the negative sign. That means the stress in the concrete is equal to the compressive stress which is generated by the effective prestress plus or minus the stress that is generated by the axial load. Here also in the expression we have not considered any non-prestressed reinforcement. If there is non-prestressed reinforcement, then the area AC is to be substituted by AC plus the modular ratio times AS, and the transformed area AT is to be calculated including AS. That is the way we have seen to include AS in the previous expressions. Similarly, we shall include AS in this expression as well. The value of Fc should be within the allowable stress under service conditions. As I said before, that the allowable stress under service conditions is different from the allowable stress at transfer, and we need to make sure that the stresses that are generated by the effective prestress and the external load should be within the allowable stress under service conditions. Next, we are moving on to the analysis of ultimate strength. The ultimate tensile strength of a section, which is denoted as PUR, that means the ultimate load of resistance, it can be calculated as per clause 22.3 of IS 1343/1980. The ultimate load in absence of any non-prestressed reinforcement is given as 0.87 times the characteristic strength FPK times the area of the prestressing tendon AP. If we have non-prestressed reinforcement, then the ultimate tensile strength is given as 0.87 times Fy times AS, which is the area of the non-prestressed reinforcement, plus 0.87 times the characteristic strength times the area of the prestressing tendon. Here 0.87 is the material safety factor, and it is the inverse of 1.15. Now, in this previous equation, Fy is the characteristic yield stress for non-prestressed reinforcement with mild steel bars, that means the bars which have a definite yield plateau, the stress corresponding to the yielding is denoted as Fy. For high strength deformed bars, Fy is equal to the characteristic 0.2 proof stress. Now, we had learned that the proof stress is the stress corresponding to a particular plastic strain. The 0.2 proof stress is obtained by drawing a line parallel to the initial modulus, and it starts with a plastic strain of 0.002. Wherever this parallel line intercepts the stress strain curve, the corresponding stress is termed as the 0.2% proof stress. Fpk is the characteristic tensile strength of the prestressing tendon. Now, once we know these material properties of both the types of steel, we can find out the ultimate tensile strength of a member. Now, this ultimate strength should be greater than the demand due to factored loads. Now, here there is a difference between the analysis at transfer and service loads with the analysis at ultimate strength. For transfer and service loads, we calculated the stresses and compared the stresses with the allowable value, whereas for the ultimate loads, we first computed the ultimate strength and then we compared the ultimate strength with the demand under the ultimate loads or the factored loads. Hence, to summarize, the computation of the stage at transfer and that at service loads is based on stresses where we use an elastic analysis, whereas the computation for the ultimate strength is based on strength and not stresses, and there we use a nonlinear material properties of the steel. Next, if we are calculating the ultimate compressive strength, then the expression in presence of moments can be found out by the use of interaction diagrams. Usually, compression members are also subjected to moments like columns. Now, if we have to find out the ultimate compressive load in presence of moments, then we have to use the interaction diagrams that we have learned under reinforced concrete. The code IS 1343 allows us the method given in IS 456 to be used to find out the ultimate compressive strength in presence of moments. For a member under compression with minimum eccentricity, we can neglect the use of the interaction diagrams, and then the ultimate strength is given by this following expression. PUR is equal to 0.4 times the characteristic strength of concrete times the area of concrete plus 0.67 times the yield stress of the steel times the area of the steel. Now, in this expression, we have considered that both the materials have reached their ultimate capacities, and also we have introduced a factor to consider the effect of minimum eccentricity, and what we find is that the ultimate strength is a summation of the compressive strength of the concrete and the compressive strength of the reinforcement steel. Now, in this expression, the contribution of prestressing steel has been neglected. Usually, the area of prestressing steel is very small and it need not be considered in considering the compressive strength of an axially loaded member. Thus, till now what we have studied is, first we studied the analysis at transfer, where we found out an expression of the stress Now, since the stress has to be less than the allowable stress at transfer, we can limit the maximum pre-stress that can be applied. Next, we studied the analysis at service loads, where we found out the stresses due to the effective pre-stress after the losses and the external load that acts on the member. Then we found out the strength, the ultimate strength, when both the materials steel and concrete are reaching their ultimate capacities, and we are comparing this ultimate strength with the demand which is coming under the factored loads. The ultimate strength has to be larger than the demand under the factored loads. Next, we are moving on to the study of an important behavior. It is the complete load versus deformation behavior of the axially loaded member. The analysis of behavior refers to the determination of the complete axial load versus deformation behavior. The analysis at transfer, under service loads, and for ultimate strength corresponds to 3 instants in the above behavior. That means whatever we have studied till now, those are just 3 points in the complete load versus deformation behavior. The load versus deformation behavior is an entire curve which shows how the member will behave when we are gradually increasing the externally applied load. The analysis involves 3 principles of mechanics. First is equilibrium of internal forces. Here, the internal forces are in equilibrium with the external loads at any point of the load versus deformation behavior. Now, this is a very important principle of mechanics, that at any time the structure is under static equilibrium. What it means is that the internal forces that are generated within the member and the external load are in equilibrium, and we can write the equations of statics for at any point of this load versus deformation behavior. The internal forces in concrete and steel are evaluated based on the respective strains, cross-sectional areas, and the constitutive relationships. Here we are learning some other new terms, that first of all, the forces are related with the strains in the individual members. It's also related with their cross-sectional areas, and also it is related with their constitutive relationships. Constitutive relationships, it is the relationships between the stress and strain for individual member. The second principle of mechanics is the compatibility of the strains in concrete and in steel for bonded tendons. This assumes a perfect bond between the two materials. This is another very important principle that we are assuming, that the concrete and the prestressing tendon and any other non-prestressed reinforcement, if they are present, they deform together. That means the strain that the concrete undergoes at the level of the steel is same as the change in the strain in the prestressing tendon, and also it is equal to the strain in the corresponding level of the reinforcement. Now, this is true when we have a bonded tendon. That means in a pre-tension member, the tendons are bonded with the concrete, and in a post-tension member, if we grout the post-tension member, then also the tendons are bonded with the concrete, and we can expect strain compatibility between the concrete and the steel. For unbonded tendons, the compatibility cannot be expressed in terms of strain, but it can be expressed in terms of overall deformation. Now, in this lecture, we are not considering unbonded tendons, we are just studying bonded tendons, where we shall assume a strain compatibility between the concrete and the steel. The third principle of mechanics is the constitutive relationships. The constitutive relationships relate the stresses and the strains in the materials. These relationships are developed based on the material properties. The first principle, that is equilibrium, can be expressed at any instant of the load versus deformation behavior by this following equation. The external load is equal to the internal force in the concrete plus the internal force in the non-prestressed reinforcement plus the internal force in the prestressing tendon. Here Fc is the stress in the concrete, Fs is the stress in non-prestressed reinforcement, and Fp is the stress in the prestressed tendons. That means the axial force which is externally applied is a summation of the internal forces that are generated within the concrete, steel and the prestressing tendon. Next, we are writing the equations of compatibility. For non-prestressed reinforcement, epsilon S, which is the strain in the concrete at the level of the steel, is epsilon C is equal to epsilon S, which is the strain in the non-prestressed reinforcement. That means what we are trying to express is that both the non-prestressed reinforcement and the concrete deform together. Hence, the strain of the concrete at the level of the non-prestressed reinforcement are same as that of the strain in the steel. For the prestressing tendon, the strain in the tendon is given as the strain in the concrete plus an additional term which is called the strain in the prestressed tendon at the decompression of concrete. Let us now try to understand this additional term in the strain compatibility equation of the prestressed tendons. The strain in the prestressed tendons at the decompression of concrete, which is denoted as epsilon DEC, is the strain when the concrete has zero strain. That means how we are defining the strain at decompression of concrete. It is the strain in the prestressing tendon when the strain in the concrete is zero. That means the concrete is no more under compression, it has been decompressed under the externally applied load. This occurs when the strain due to the external tensile axial load balances the compressive strain due to prestress. That means whatever strain the prestress is applying on the concrete member, the external load is applying an equal and opposite strain, and hence the strain in the concrete is finally equal to zero. For pre-tensioned and post-tension members, the values of epsilon DEC are different. The reason behind this difference is the different way of applying the prestressing force. Next, we are moving on to the third principle of mechanics, which is the constitutive relationships. The constitutive relationships can be expressed in the following forms based on the material stress strain curves shown in the module of Introduction Prestressing Systems and Material Properties. For concrete under compression, we have an expression which is equal to Fc is equal to some function of epsilon C. We are writing that function as F1 of epsilon C. For prestressing steel, the relationship can be written as Fp is equal to some function of epsilon P, and we are denoting this function as F2. For reinforcing steel, the constitutive relationship can be written as Fs is equal to some function of epsilon S, and this function is denoted as F3. Let's try to understand this constitutive relationship for each of the members individually. The stress versus strain curve for concrete is shown in this figure. Here, the first quadrant, or the quadrant at the top right, represents the behavior under tension. That means once the concrete cracks, we are not considering any stress in the concrete, and this part of the curve in the first quadrant can be considered to be linear elastic, where Fc is equal to Ec times epsilon c. The third quadrant, which is the lower left quadrant, represents the behavior under compression, where the behavior is a parabolic form, and we have seen the expression of Hognestad's equation for normal strength concrete and the expression by Thorenfeld, Tomasovich and Janssen for high strength concrete, and we can use that expression to get the functional form relating Fc and epsilon c. Now, once we have these two equations in hand, we can write this generic expression Fc is equal to F1 times epsilon c. That means for a certain values of epsilon c, for positive values of epsilon c, we are using the linear elastic relationship. For a negative value of epsilon c, we are using the relationship for concrete under compression. The second considered relationship is for the pre-stressing tendons, and we are considering only the relationship for tension, and here we see that initially the pre-stressing force is almost linear in elastic, and then we have a curved behavior till it gains its ultimate strength. Now, the variation of epsilon Fp with respect to epsilon p can be given in the form of a curve in a graphical paper, or it can be given in the form of a table, or we can try to fit some equation for the different regions of the strain. Now, once we have either one of these forms, we say that we are able to express the stress Fp in terms of epsilon p in this functional form, which is denoted as by F2, that is Fp is equal to F2 of epsilon p. The third constitutive relationship is for the stress strain curve for reinforcing steel, and here we have shown the behavior both for the tension quadrant and the top right and for the compression quadrant, which is for the bottom left. We see that for either of the quadrants, the behavior initially is elastic. Then for this mild steel, we have a definite yield plateau, and then we have a strain hardening region till it reaches its ultimate stress. If we do not have mild steel, then we will not be seeing this yield plateau, but we will have a curve which again will be given in either a graphical form or in a tabular form. Now, this relationship between Fs and epsilon s is expressed in terms of this equation that Fs is equal to F3 times epsilon s. That means this functional representation of the constitutive relationships imply that given a strain in the material, we are able to calculate the stress. Now, the calculation of the stress can be from either an analytical expression like a parabolic expression, or it can be from a graphical form where the material behavior is given as in a graphical representation, or third, we can have a tabular form where the values of stress are tabulated against the values of strain. Once we are able to determine the stress corresponding to a strain, we say that we know the constitutive behavior of a particular material. The equilibrium and compatibility equations and the constitutive relationships can be solved to develop the axial force versus deformation curve. Now, here we have seen a set of equations. First, we have seen an equilibrium equation where the external load is equal to the summation of the internal forces. Next, we saw a set of compatibility equations where for the reinforcement steel we saw epsilon S is equal to epsilon C. For the pre-stressing tendons, we have seen epsilon P is equal to epsilon C plus epsilon DEC, and then we had three equational forms for the constitutive relationships, that Fs is equal to a functional form of epsilon S, Fc is equal to a functional form of the epsilon C, and Fp is a functional form of epsilon P. Now, once we have this set of equations, these equations can be solved simultaneously, say for a particular value of epsilon C. For a particular value of epsilon C, we can calculate epsilon S, epsilon P, from which we can calculate Fs, Fp and Fc, plug them in the equilibrium equation, and we get the axial force P. The axial deformation is given as epsilon C times L, where L is the length of the member. That means for any value of epsilon C, we can determine a value of P and a value of the axial deformation. The following plot shows the axial force versus deformation curves for a pre-stressed and a non-pre-stressed sections. Here, the two sections are considered to be equivalent in terms that their tensile strengths are same. The orange curve is the axial force versus deformation curve for a section without any pre-stressing tendon. It is just reinforced with conventional steel, and what we see is in the tension quadrant, the axial force almost increases linearly with deformation till the member cracks. In this region, the elastic analysis is applicable, and then when it cracks, there can be a drop in the axial force till the system comes under equilibrium, and again the axial force increases with deformation, but this time it increases with a lower stiffness. That means the rate of increase of the axial force with deformation is low as compared to the pre-cracking behavior. And finally, when it reaches the tensiles, when it reaches the yield stress of the steel, then the increase in the axial force can be negligible, and that instant is called that the member has achieved its ultimate tensile strength. On the other hand, if we look into the behavior in the compressive quadrant, then we see that initially the behavior can be almost linear elastic, but then we see a nonlinearity due to the nonlinear behavior of the concrete. Now, these curves are a schematic representation of the axial load versus deformation behavior. The exact nature depends on the equations that we are using and the type of steel that we are having. Now, compared to a non-pre-stressed section, which is represented by an orange line, let's observe what happens to a pre-stressed section, which is represented by the blue line. The first thing we see that the pre-stressed section has a curve which has been offset from the origin. What it means is that at zero external force, we have some negative deformation, and that is true. That means under the pre-stressing force, we have an axial compression in the member. Next, we are increasing the level of the axial force, and we are achieving a zero deformation for a certain value of the axial load. What it means is that we need to have some external load, external tensile load, to have zero deformation in the member, and that instant is called the decompression of the concrete. Then the axial force increases with the deformation till it cracks, and what we observe is that this cracking level is much higher compared to the cracking level for a non-prestressed section. That is the beauty of a prestressed member, that the cracking level is much higher than the non-prestressed member. Now once it cracks, then the behavior is similar to reinforced concrete member, that there will be an increase in the axial force with deformation, but with much reduced stiffness. That means the increase in axial force with deformation is now much lower till it achieves a ultimate strength, beyond which it may stay constant depending on the type of steel. On the other side, if you are applying compressive load, then we see that the behavior is similar to reinforced concrete, but it does not achieve the same compressive strength as that of the reinforced concrete, because here the concrete is under a pre-compression, and hence it reaches its ultimate strength at a lower external load. Now this two curves gives the essential difference between a reinforced concrete and a prestressed concrete member. Now let us try to understand them with some logical statements. The first one, what we have understood is that the prestressing increases the cracking load. See, again in the first lecture I had said that why is concrete prestressed at all? The basic reason is that concrete is weak in tension as compared to compression, and to check the cracking of concrete, to make up for the weakness of concrete under tensile load, prestressing is done, and once we prestress a member, the cracking load is increased. Next inference we have is that the prestressing shifts the curve from the origin. The two analogous statements are, the first one is, for the prestressed member there is a compressive deformation in absence of external axial force. What we can see that even if there is no external force in the prestressed member, there is a compressive deformation in the axially loaded member, because that comes due to the effect of the prestressing. The second corollary is a certain amount of external load is required to decompress the member. That means we need some external load to have zero strain in the concrete. These two are unlike reinforced concrete. In reinforced concrete, if there is no external load, then there is no strain in the member, and also we do not need any external load to have zero strain in the concrete. The third corollary is, for a given tensile load, the deformation of the prestressed concrete member is smaller. If we go back to this curve and if we pick up any axial force, what we see corresponding to an axial force, that orange line is much shifted from the blue line along the deformation axis. What it means is that the deformation of the reinforced concrete member is much higher as compared to a prestressed concrete member for a given level of the axial force. Thus, the corollary is prestressing reduces deformation at service loads. Now, this is an important benefit of prestressed concrete members, that if we prestress a member, then we will have less deformation under service loads. The fourth inference is, for a given compressive load, the deformation of prestressed concrete member is larger, From these two curves, what we observe that for a given axial force, the blue line is shifted from the orange line on the left hand side. That means the deformation of a prestressed concrete member under compression is more than the deformation of a corresponding reinforced concrete member. We can conclude that prestressing is detrimental for the response under compression. The fifth inference is the compressive strength of the prestressed member is lower. See, we have taken two sections which have equivalent tensile strength. What we find is if we prestress, then the strength of the prestressing member is lower. Hence, we can see that prestressing is actually detrimental for the compressive strength. Now, the sixth inference is for a partially prestressed section with the same ultimate strength, the axial load versus deformation curve will lie in between the curves for prestressed and non-prestressed sections. What we are saying is that this orange line represents the curve for a reinforced section, the blue line represents the curve for a prestressed section with both of which have equivalent tensile strength. If we pick up a partially prestressed section which has both prestressing tendons as well as reinforcement, then and if the partially prestressed section is also of the same tensile strength, then its axial load versus deformation curve will lie somewhere in between this orange and the blue lines. These above conclusions are generic for prestressed members. So, the purpose of studying this behavior under axial load was to understand the essence of prestressing with compared to reinforced concrete structures. And these observations are similar for any other prestressed members such as members under flexure. This material has been taken from the book Prestressed Concrete Structures written by Collins and Mitchell. Thus today we studied the analysis of members under axial load. First, we studied that the analysis of members of axial load can be very few and far between because we do not have members which are purely under axial load very frequently. We may have some hangers or ties which are under axial tension. We may have piles which may be under axial compression or axial tension, but usually piles are also subjected to moments and shear. But the whole purpose of studying the behavior of members under axial load is to understand the difference of the prestressed members and reinforced concrete members, and it gives us a foundation to understand the analysis procedure for members under flexure. First, we studied the analysis at transfer, where we have found that based on the allowable stresses at transfer, we can determine what is the maximum amount of prestressing force that we can apply. Next, we studied the analysis at service loads, where we determined the stresses from elastic analysis from the effective prestressing force after the long term losses and the external characteristic loads. What we should maintain is that the stresses under this effective prestressing force and external loads should be within the allowable stresses under service. A member can be either fully prestressed, where we do not take account of any non-prestressed reinforcement for the strength, or a member can be partially prestressed, where we take advantage of non-prestressed reinforcement also. We studied the analysis of ultimate strength, where we found out the maximum capacity of an axially loaded member. It can be either the tensile strength or it can be the compressive strength, and this strength has to be larger than the demand that comes from the external factored loads. Next, we moved on to the analysis of behavior, where we studied the complete load versus deformation curve of an axially loaded member, and we have seen that this needs three principles of mechanics. The first is the equilibrium of forces, which means that the external load is equal to the internal forces that generates in the concrete, in the reinforcement steel and the pre-stressing tendon. The second is the compatibility relationship, where we have seen that the strain in the steel is related with the strain in the concrete. For the non-pre-stressed reinforcement, the strain epsilon s is equal to epsilon c of the concrete at the level of the steel. For the pre-stressed reinforcement, epsilon p is equal to epsilon c plus epsilon dEc, where epsilon dEc is the strain at decompression of concrete. This is a new term which we learned, that the strain at decompression means it's the strain in the pre-stressing tendon when the concrete has zero strain, and the expression of epsilon dEc is different for the pre-tension members and the post-tension members. For the pre-tension members, epsilon dEc is equal to epsilon pi, which is the strain right before the cutting of the tendons, and for post-tension members, epsilon dEc is equal to epsilon p naught after transfer plus the strain in the concrete. Now, when we solve these equations, we get the complete load versus deformation curve, and we have seen for a pre-stressed member, the curve gets shifts from the origin, the cracking load is higher, the deformations under service loads is lower compared to a reinforced concrete member. Pre-stressing may not be beneficial for compression. Now, this difference between the reinforced concrete and pre-stressed concrete are quite generic, and it will help us to understand the behavior of members under flexure. In our next class, we are moving on to the analysis of members under flexure. Thank you.